Hello, this is the second video of the performance analysis of a Tesla Model 3 electric motor series. Today I will be using the standalone version of MotorXP-PM. In this video, I will tell you about the DQ model of the motor and how it is used for steady-state DQ analysis in MotorXP-PM. Steady-state DQ analysis allows us to create different performance curves of the motor, such as torque versus speed, torque versus advance angle, and many others. Additionally, we can generate performance maps of the motor, such as efficiency map. I have already used steady-state DQ analysis in the first video of this series, but all calculations were done using FEA-based model type. In order to use other model types, the DQ model of the motor should be built. It significantly speeds up the analysis. Now let's create a separate project file for DQ analysis. Let's open Design Studio and make some changes before starting to build the DQ model. Since the DQ model does not take into account the cogging torque, the number of mesh slices can be set to 1 and the rotor skew angle to 0 degrees. This will reduce the time required to build the DQ model. Convergence tolerance is the first parameter to define before building the DQ model. 0.01 is enough in most cases. Let's set the maximum RMS supply current to 1200 amperes. Current step and advance angle step are the two parameters used to define the accuracy of the DQ model. A smaller step size will increase the accuracy, but will also increase the time required to build the DQ model. Before I start building the DQ model, let's evaluate how DQ model parameters depend on the current and advance angle to choose the appropriate step sizes for the current and advance angle. Let's use the steady-state DQ analysis plot wizard with the FEA-based model type and plot the LD inductance, LQ inductance, and D-axis magnet flux linkage versus current. The current range is from 0 to 1000 amperes. Let's use a step size of 20 amperes to obtain smoother curves. As it was determined in the first video, the advance angle of 55 electrical degrees produces the peak torque at the maximum current. Let's use this value. The results are ready in 4 minutes and show how the DQ model parameters vary as the current changes. The current step for building the DQ model may be determined depending on the operating current range and required accuracy. This picture demonstrates the piecewise linear approximation used for the linearized DQ model parameters interpolation. In this case, the current step size of 100 amperes will provide a good approximation. Let's use a step size of 100 amperes for the current. Similarly, curves of the DQ model parameters versus advance angle can be obtained. The nonlinearity of the DQ model parameters increases with high current, so the current of 970 amperes will be used. In the first video, the current of 970 amperes was determined as the maximum current of the motor. The advance angle range is set up to a maximum of 360 degrees with a step size of 2.5 degrees. The results are ready in 11 minutes, showing how the DQ model parameters vary as the advance angle changes. Since the motor operates with the advance angle range from 0 to 90 electrical degrees most of the time, the advance angle step size for building the DQ model will be determined for this range. The step size of 10 degrees seems to provide a satisfactory accuracy for the piecewise linear approximation. So let's use the advanced angle step size of 10 electrical degrees. Since the DQ model parameters are also dependent on the rotor position, it is recommended to use at least 2 rotor positions, which is good enough in most cases. Now I can build the DQ model of the motor. Sometimes the solution may not converge and a dialog box like this will appear. This may occur if the BH curve of the iron material contains measurement noise. You may either use another material or change the non-convergence hanging setting to ignore non-convergence and continue simulation. The DQ model is now ready, which took 28 minutes. Now I can analyze the motor characteristics in seconds since I can use the fast DQ model of the motor instead of the slow FEA-based model. Let's plot some motor characteristics across the speed range up to 16,000 RPM with a step size of 50 RPM. Let's use a current of 970 amperes and an advance angle of 55 degrees as determined in the first video. In order to define the motor operation in the field weakening region, let's set up the maximum voltage provided by the inverter as calculated based on the DC voltage and PWM method. Now let's open the drive setting and set up the parameters of the drive. As shown here, the maximum RMS phase voltage will change as I change the drive settings. Let's set up the DC voltage to 345.6 volts, PWM method to space vector PWM, and the PWM frequency of 10 kHz. The field weakening control is set up as maximum torque with limited current, so the current of the motor does not exceed the limit specified by the RMS supply current field. Let's plot current, voltage, torque, advance angle, efficiency, and power factor. Model type, DQ with sinusoidal supply, and the interpolation method is linearized, which is a piecewise linear interpolation. Click the plot button. Results are ready in 45 seconds. Some oscillations of the motor parameters are caused by the piecewise linear interpolation of the parameters of the DQ model. Changing the interpolation method to nonlinear should eliminate these oscillations. The calculation with nonlinear interpolation takes a bit longer, and in this case took 1 minute and 5 seconds. It is interesting to notice that about 6,500 RPM and above, the motor enters the field weakening region, as the inverter voltage reaches its maximum and the advance angle starts to increase to weaken the magnetic field of the magnets. Above about 10,000 RPM, the current starts to decrease since the back EMF of the motor becomes so high that the inverter is no longer able to supply a current of 970 amperes. Now let's plot the torque versus advance angle characteristics of the motor for several current values. In the first video, this took several minutes to calculate the FEA-based model. With the DQ model, it takes only a couple seconds even with a step size of 1 electrical degree and nonlinear interpolation. Now let's look at another option of the steady-state DQ analysis, performance maps. Performance maps allow us to study the performance of the motor across the entire operating range with the chosen control strategy, either maximum efficiency or maximum torque per ampere per volt operation, taking into account field weakening. The well-known example of a performance map is an efficiency map. Advance angle ranges from 0 to 90 degrees corresponds to the motoring mode. Advance angle step size and the DQ model parameters interpolation method define the accuracy of the mapping. The default advance angle step size is 1 degree. Maximum voltage current and speed define the operating limits of the motor. The maximum RMS phase voltage provided by the inverter can be either entered manually or determined automatically based on the PWM method and DC voltage. Let's set up the maximum RMS phase current to 970 amperes as it was determined earlier and the maximum speed of 16,000 RPM. Maximum input power is an optional parameter and may be left empty. Mechanical losses can also be included into analysis by defining mechanical loss coefficients. An empty mechanical loss coefficients field used in this case assumes that no mechanical losses are considered. Let's use the torque step of 20 Newton meters and speed step of 100 RPM. Now let's select maps to be plotted. I would like to plot the efficiency map of the motor, current, voltage, and advance angle. The selected maps are plotted, which took about 3 minutes. Once the performance maps of the motor are calculated, the data can be used to design the motor control. Tables of ID and IQ current components corresponding to the optimum motor performance across the entire operating range can be exported into separate files and used for the motor control design. Our customers report at least 10% improvement in the motor performance when ID and IQ lookup tables from MotorXP-PM are used to control the motor.